this is another problem. So if we start with an x, which is basically a vector of elements x0 to x7, what we want is to compute this xi, which is basically, let me write it up, it's x1 till x7. Okay, so this is a reduction because we start from a vector and then we want a single value. The idea here is to try and fold elements, try to split x in some way, add them, and then do this n steps until we have the sum in one element of x. Okay, so this is what we do in these instructions. We basically shift the vector, sum it against itself, shift it another time, then sum it, shift it, and sum it. But these instructions are really weird. That's why I'll try to explain in this stream. So the first thing we do is this MM256 permute to F128 PS. What is this? Okay, so step one, nicer color. So step one, we do this permute stuff. MM256 permute to F128 PS. Okay. So if we take a look at the Intel intrinsics, there's an intrinsics guide that I use to understand this stuff. To F128 PS. This D is for double, S is for single precision. So shuffles 128 bits, floating point, selected by an IMM8 from A and B, and stores the result to destination. Okay, so this is hard to parse. Took me some time to understand this. So I'll try to break it down. What this does is basically concatenate two 256 vectors and use a permutation instruction to permute elements of these vectors into a resulting vector. So what is a permutation of elements? We have a simpler version of permute, which is basically just permute PS. So this shuffles a single position floating point element in A. Okay, so A is going to be an M256, which is the vector of H floats, and then we shuffle them using an IMM8. Okay, this is a really rich instruction. So basically what we do is the following. Okay, so let me parse this instruction. So we use an IMM8, which is just a control sequence of 8 bits. So let me start with 8 bits. Let's say 1 in 8 bits is just the following: 2, 2, 4, 6, 8. Yeah, so this is the first sequence, and then our vector is x0 x1 till x7. Okay, but the trick here is just that this permutes within 128 bit lanes. But the problem here is that x is 256 bits. So we permute each 128 lanes separately. So we separate this into 2 from x1 to x3 and from x4 to because this is 128 bit, this is 128 bits. So we shuffle them using the same IMMH bit separately. Okay, let me add a new page. So I'll try to write it up nicely. We have this control sequence. We have our x. Let's index into our x. Let's start with x0, x1, x2, x3, x4, x5, x6, x7, and then our control sequence. So 1 can be represented as the following, but keep in mind this is IMMH, so we have to reshuffle the orders of the bits of ones. Sorry. So this is we split them in two. This is index 0, index 1, index 2, index 3, index 0, index 1, index 2, index 3. Okay, so this is represented as the following: 0, 1, 0, 0, 0, 0, 0, 0, and this is 0, 1, 0, 0, 0, 0, 0. You can see here that we moved from a representation IMMH which flips the bits of the control sequence. So what the instruction permute does, it just basically points to values into the 128 bit lane to shuffle. So what this tells us is that this is the first 0, 1 is basically 1, because we have 2 bits. We can represent the positions till 4. So we have 0, 1, 2, 3, 4, because we have 2 bits of elements. This is a basic match. So 0, 1 points to index 1, 0, 0 points to index 0, 0, 0 points to index 0, 0, 0 points to index 0. We have the same thing here. We didn't change the sequence. So this basically is this. So the result of this permutation is the following. So index 0 points to x1. So we have x1 here. Index 1 points to x0. So it's x0, x0, x0. And the same thing here. We have x5, x4, x4, x4. So we moved from a vector of x0 to x8 to this vector. This is the result of the permutation. And using this permutation, we can do this shuffle stuff, which makes it possible for us to shuffle the star chain vector, add it add each vector to itself, and then have the result of the addition. The result of the addition will makes it possible to add all the elements of the star chain vector into a single floating point element. Yeah. So we get our sum. Okay. So I guess this is clear now. So now we'll come back to our wheeled instruction, which is the MM256 load PS. Okay. Here you go. MM256. Yeah. MM256 permute to F128 PS. So this takes 256 value lanes, but each one is packed, shuffles 128 bits. So we take 128 bits at a time. So we shuffle 128 bits at a time, which is quite different from shuffling a single 32-bit. Okay, so basically we take four values. We shuffle 4 values from four values. This is why we need A and B, because A is basically two values of 128 bits. B is the same. So if we put A and B next to each other, we can see that it's basically 4 128 bits values that we shuffle using the same thing. So this basically just uses the same permutation instruction but into a higher order vector, so we can shuffle 128 bits at a time. Okay, it's quite powerful. So let me illustrate this. So if we represent A as, so A is 256 bits. Sorry, I'll try to use another color. So A is 256 bits. So A can be divided into 228 bits, A1 and A2. B is the same, 256 bits. So we can represent it as B1 and B2. Okay? To simplify this a little bit more, we can see that we apply this permute to F128 to the same SIMD vector. Okay? So what this means is just that A is equal to B, which means we can replace this with the following: A1, A2. Each one of them is 128 bits, and this is what we shuffle. Okay, so if we draw the same thing as we did before, this control sequence, we can do the same logic but 128 bits at a time. So we have our control sequence. I'll try to write it after. We have our A and B, which is basically A1, A2, A1, A2, because that's what gives us 428 bit lane. And then we use the control sequence. We can see here that we use 1 as a value, which is an IMM8, which is the same thing as the thing we did before, which is this sequence. This is the same. 1 can be represented in binary as the following, and then we use it the same way. So we can represent this control sequence as the following, because 1 can be represented in binary as this. I guess I'm missing a 0. Yeah. So the result is the following. So we check A and B, this control sequence. This points to this, this points to this, this points to this, this points to this. This stuff of representing zeros is just basically we're saying yeah, we don't mind if the rest of the sequence contains just point to the first element, which means we will discard them either way. So I'll try to write it in a way that makes sense. So the result is this: A2, A1, A1, A1. Yeah. So this is the shuffler in result, which I'll try to call P1. P1 is this vector. Okay. So if I rewrite P1 in the elements of X, which is our start, so X is basically this sequence: X0, X1, X2, X3. So this is A1, X4, X5, X6, X7. This is A2. So P2, which is the result of 1, is the following: it's X4, X5, X6, X7, X0, X1, X2, X3. So we basically permuted 128 bits of A, doing this trick. Okay. So the next thing we do is just sum the starting vector with this shifted vector, with this permuted vector, and this is a very simple instruction. It's just a vectorized add between the elements of A and B. So we put X here. This is our second step. Try to write it in nicer color. So our second step is just add x and p2, which means that x plus p2 is basically this, x0 plus x4, okay, x5 plus x1, x6 plus x2, this is a comma, and x7 plus x3. The rest is basically the same because we just shifted it, so it's basically the same as this. Okay, so this is our first step. Yeah, so this is 128 bits. This is 128 bits, and it's basically the same vector. What we are trying to fold now is a 128 bits vector. Try to sum all its elements. So we moved from summing the elements of 256 bits vector, which is 8 floats, to summing the elements of 4 floats. Okay. So same trick again. Okay, so this is what we did before. Now we need to shift the elements of this sum, which is x plus p2, in our using this instruction. So this instruction is the first instruction I showed, I broke down to explain the permutation 128 bits. But we use 14. Yeah. So 14 in binary. Let me start Python repeat. So bin 14 can't write is this. Okay. So the third step we do is this mm256 permute ps of x plus p2. Okay. Using this control sequence of 14. So 14 in binary as IMMH is so this gives us 4, yes, and this is the rest. Okay. I'll try to name the elements of this vector as a1, a2, etc. to not be confused. So this is basically let's call it yeah, so this is S1, this is the first sum. So we call this V1, V2, etc. V4. So the sequence we okay, so let me call this V. So what we are trying to shift, so this is the control sequence. If we write it, it's 1 0 1 1 0 0 0 0 1 0 1 1 0 0 0 0. Okay. And this is the V. The V is basically V0, V1. Sorry, so I start indexing from 0, like a real computer scientist. V2, V3, V4, V5, V6, V7. Okay. And then what does this stuff points to? So basically the trick is that we discard this. This we don't need because this is the elements that are here. Okay. So this we don't need. The elements we need to shuffle are those elements. So 0, 1 is basically the third index. So if we index here, so this points, it could point to V3 or V2. It's either way, because when we shuffle it here in the result, we need to add V0 either to V2 or to V3. It's the same. So this points to index 2, this points to index 3, and this points to this. So the result is this. We have V2, V3, V0, V0. Okay, and we call this permute 3. This we don't mind because we just need to sum the 128 bits lane. It's still a 256 bits vector, but we just need to need the first half of the vector. Okay. So the result of this, just to be sure I check my notes. So the results of this is the following. Let me. So we shuffled the first elements, and then we start with V2, V3, which are, so P3 could be represented as the following. We start with V2, which is XX plus X2, X7 plus X3, and then we point to V0 with X0 plus X4, X0 plus X4. Okay, the rest we don't care about it. And then if we take a look at the code, we just same instruction, vectorized add of 256 bits with the first element we started with, which is our X. Sorry, not the first element, with the result that we permutated, which was this stuff here, X0 plus X4, X5 plus X1, etc. So this is what I called sum1, which is X0 plus X4, X1 plus what is it, X5. The rest we don't really care about because we shuffled it. Okay, so this gives us our sum2, which is X0 plus X2 plus X4 plus X5, X6, and this is the pair values, and this is the odd, sorry, the odd values. This is the can't seem to recall the name in English. So X1 plus X3, X5, X7, and the rest we don't really care about. Okay, so this is only 64-bit. So we moved from from summing 256 to 128 bits. So S2 is still a 256 bits vector. It's just that we discard the rest because we don't need it. We will sum all the values using vectorization in the first element of the sequence. Okay, so this is quite a nice trick. So SIMD instruction how to do this is really nice. We could maybe reshuffle it, reshuffle it and then add it, but there is a nice trick. Is that SIMD instructions are either work either vertically or horizontally, which means that we can either vertically add just this add stuff. This add stuff takes two vectors, and then I add each element of the vector in one instructions. We could also have the horizontal equivalent to this instruction, which horizontally adds elements of the two vectors and then put them in the same vector. This is a really nice trick. So if we take a look here at how this is done, if we take horizontal add, let's say two vectors. I'll try to be brief here. X1, X2, X3, X4, and then we have, so this is our X and our Y. This is just 4 floats, but the same logic applies to bigger CMD vectors. Y4. What we do here when we do an H add between the two is just we sum those two elements, these two and these two. Okay, and the result is the following. We put the first in the first, so this is basically a vector of 4 floats. Sorry. So we put the first here, then we put the second here, then the third here, then the fourth here, which means we will have x0 plus x1. Here is y1 plus y2. This is x3 plus x4, and this is y3 plus y4. So this is quite different from just add summing the elements, which if we do a normal add between x and y, vectorized add, we will have the following. We will have x0 plus y0, x0 y1 plus x1, etc. So this is really different from this. And this trick of horizontal add is really useful when doing stuff like I guess complex number arithmetics, which we need to add the elements horizontally. And this trick is useful for doing our add. So if we go back to our result S2, our S2 is here. Sorry. So I'll try to rewrite it. Yeah, so this is our S2. Boom. And yeah, so we basically do the horizontal add of this S2 and itself. So these are the even elements of the vector x1 plus x2 plus x4 plus x6. These are x1 plus x3 plus x5 plus x7. The rest we don't really care about. So if we do a horizontal add, which is our fourth step, come on, fourth step, we do an MM256 horizontal add between S2 and S2. This means, let's try and represent S2 as this is S21, S20, S21, etc. So we'll have S20, S21, S3, S22, etc. We'll have the same thing here, S20, S2, no, it's not gonna be 0. Sorry, it's me right here. So S24, S25, S26, S27. And then we do a horizontal add. That's what I explained before. We do this stuff, this stuff here. So the result is the following. This first addition, we push in the first element of the vector, which is S20 plus S21. That's what we want. That's our sum. The rest we discard. We don't really care about it. Okay? So the sum here, the last sum, is a vector which contains x, write it in terms of x. So we sum all the first elements here with these elements, which means we sum all the elements of x. So the first element of the result is going to be the sum of xi, I going from 0 to 7. The rest we discard. We don't really care about it. And that's what we do here. So initialize an array of 8 floats. We store the vector in this in the pointer of this result, and then we return the first value of the vector. Yeah, so this is why we get this kind of performance. It's quite convoluted, but it's fast. Okay, so I hope that explains